Hello everyone. Welcome to this webinar on the alchemical free energy simulator module in our MolCube-Builder product. My name is Yunwen Tao. I'm a computational chemist working at MolCube. In today's webinar, I will walk you through different components of the alchemical free energy simulator, AFES module, and demonstrate how to use them. In the current drug design and the discovery pipeline, FEP calculation is an important tool used in the lead optimization stage. Here, the term FEP is not limited to free energy perturbation method, but it is a broad term, and it stands for a series of alchemical free energy calculation methods. In the lead optimization process, if we want to rank the binding affinities of lead analogs, we can conduct relative binding free energy calculations, the RBFE. The central idea of RBFE is the thermodynamics cycle. This cycle converts the challenging problem of calculating direct binding free energies of two ligands into a manageable problem of mutating these ligands alchemically. Actually, many emerging variant methods we will cover today are still derived from this idea. In today's webinar, I will first introduce the general workflow of AFES in MolCube-Builder. Then I will introduce the three different methods supported in AFES, including the multi-site lambda dynamics in the Blade program, the alchemical transfer method, AToM, implemented via OpenMM, and the thermodynamics integration, TI method, in Ember program. In addition, I will briefly talk about our future plan on the AFES module. Here is the general workflow of the AFES module, which is very similar to the free energy calculator, FEC module in the CHARMM-GUI. We start from a PDB structure of the protein ligand complex. This structure is usually fetched from the RCSB protein databank. It can also be the structure taken from a snapshot from AMD simulation. This PDB file is first uploaded to the PDB reader to process so that the protein and the native ligand are parameterized with corresponding force fields. Then it goes through the solution builder module to add the water box and ions into the system. In the meantime, the user needs to provide the SDF files of the lead analogs. These ligand structures will be pre-processed in the ligand modeler module to make sure that they will have consistent conformation and position as the native ligand. However, since the ligand modeler module is not available at this moment in the MolCube-Builder, we assume the SDF files uploaded by the user have been pre-processed. Then AFES will take the solution builder output and the user's ligand SDF files as input to build the protein plus ligand system and the ligand solvent system. AFES module will automatically prepare all necessary input files and scripts for the user to run alchemical free energy calculations directly on GPU devices. Therefore, the main advantage of our AFES workflow is that we can easily build the simulation system and the necessary files to run alchemical free energy calculations to obtain the delta G values. The modular design of AFES makes it highly integrated with other MolCube-Builder modules. In addition, we can combine different force field parameters for protein, ligand, and water model with higher flexibility. Next, I will go over three alchemical free energy calculation methods supported in the AFES module. The first method is multi-site lambda dynamics, MSLD. Its original formulation is called Lambda dynamics, which was developed by Professor Charlie Brooks at the University of Michigan. The difference between lambda dynamics and conventional AVP is the following. In conventional AVP, we define a virtual transformation path connecting two ligands as the endpoints. Along this path, denoted by the scaling factor lambda, we gradually turn off the interaction of ligand A, but turn on the interaction of ligand B. For each point on this path, the lambda value is fixed during the MD simulation. However, in lambda dynamic simulation, multiple ligands are treated as a hybrid ligand structure with the shared core scaffold attached by multiple different substituents. Each substituent is assigned with a different lambda variable, and this variable is dynamic and could change within a given constraint. Okay, so this is the brief idea of lambda dynamics. The multi-site lambda dynamics is an extension of the lambda dynamics. It allows us to change substituents at different regions in a molecule. In this way, we can have different combinations of substituents covered in one MD simulation. Therefore, it is obvious that the MSLD method is far more efficient than the conventional FEP method. In conventional FEP simulation for just one pair of ligands, we need around 100 nanosecond simulation if we use 0.05 step size for lambda, and each lambda runs about 5 nanoseconds. However, in MSLD method, we only need 200 to 250 nanosecond simulation to cover 5 to 30 ligands with just one simulation run. Nowadays, only 2 programs can run MSLD simulation. One is the standalone Blade program, which is an open source code developed by Ryan Hayes, who is now a professor at UCI. The other is CHARMM code, which is only available to academia and in the commercial package Discover Studio. In our AFES module, we use the Blade program as a target MSLD engine and prepare necessary input files for it. In AFES, the MSLD preparation section consists of 4 major steps. If the ligand force field does not have fixed atom types, like in the case of OpenFF, we need to unify the atom types for a given series of ligands. Then our algorithm automatically identifies the core fragment and attached substituents with little assistance from the user. The charge renormalization step will adjust the atomic charges in a way that all substituents at one site have exactly the same net charge value. Then the hybrid ligand structure is built, and it is placed either inside the binding pocket of a protein to construct the complex system, or simply in the water to construct the solvent system. Next, I will show you how to use AFES module in MolCube-Builder to set up MSLD simulation and run it on a Linux machine with GPU. The example system we use here is a protein tyrosine phosphatase 1B, abbreviated as PTP1B. Its PDB ID is 2QBS. This shows the native ligand in its binding pocket. In this demo, we use 6 ligands taken from the MSLD benchmark study by the Brooks Research Group. To prepare the ligand SDA files, we use some script to automatically adjust the conformation of the ligands and align them towards the native ligand. Another possible way is to directly modify the ligand structure using molecular modeling tools like PIMO, MOE, Gauss view, and so forth. We need to note that the negative charge on the oxygen atoms has to be denoted in the atom block within the SDF file. After the preparation, the ligands from the user need to nicely overlay with the native ligand in the binding pocket. Next, we can use MolCube-Builder to set up this MSLD system. First, we create a PDB reader project. We give it a title as 2QBS-CHARMM. Here, we select CHARMM-36M as the main force field. It decides the force field for the macromolecules, including protein, nucleic acids, and membrane. We can also select the amber force field here. However, we have to use AFES14SB for protein and TIP3P model for water in order to set up the MSLD simulation. In this demo, I will simply select CHARMM as the main force field. Then we load the PDB structure from the RCSB database and put the PDB ID as 2QBS so that it is used as a starting point. In this step, we need to select the protein chains and the native ligand we want to include in our model. In this case, there is only one peptide chain and the native ligand, 024. We can inspect the native ligand 2D structure after selecting it. For the ligand force field, we just use the default OpenFF-fast to parameterize it. We don't need other crystallized water, so we only select these two things. Then we submit the PDB reader job. On the last page, we can preview the structure of protein plus the native ligand. Then we need to use the solution builder to add a water box and ion. So we click the solution builder button. In the first step, it asks for a finished PDB reader project as the input. Remember that the PDB reader project we just completed uses the CHARMM force field, and it will be shown as the top one in the following list. We click the select button and give a title for this solution builder project. We use 2QBS-CHARMM-solve. On this page, we just use the default options to decide the size of the water box and the types of ions. Here, we need to make this neutralize only option unchecked because we want to have both cations and anions in the system. After this step, the solution of protein plus the native ligand has been built. Next, we use the alchemical free energy simulator module. We select the blade program as the MD engine, MSLD relative binding as a simulation type. Then we load the solution builder we just completed. For the title line, we put PDB-1B-2-MSLD. Then we need to select the native ligand we want to replace. Here we choose HETA-024. Then more options will pop up on this page. We can first upload the SDF files we just prepared. Please note that the file names need to use the same prefix followed by numbers at this moment. Next, we need to select the force field for the uploaded ligands from user. We can select OpenFF or GAF or their accelerated versions, denoted as suffix -fast, with machine learning-based atomic charges. In this demo, we will choose OpenFF. If the substituent part has fused ring structure, we need to check this option to consider the complete ring structure in MCS searching. In this case, we don't check it. On this page, it shows the status of ligand parameterization. If we see the green check symbol here, it means the ligand is successfully parameterized. We can also check the 3D structure by clicking this down arrow icon. Then we proceed to the next step. On this page, user can adjust the definition of the core scaffold fragment by excluding certain atoms. We can first click this Select All button. Then all allowed atoms are highlighted with red color. This defines the core fragment. By clicking the atom or the button here, we can exclude certain atoms if necessary. You may be uncertain if you do this for your own system. However, I share two rules of thumb here. First, make sure all atoms within the core scaffold are fully connected. In other words, we don't want to have dangling atoms. Second, if there are different functional groups attached on the same ring scaffold, treat the major part of this ring as substituent instead of core scaffold. In this case, the current definition of core part is reasonable, and we will keep it as is. In the bottom part, we can set the MSLD simulation temperature, and we use 300K. Then hit Submit. If things go well, we will see this page to preview the complex system and the solvent system. Then we hit the Download Project button to download all necessary input files and scripts to run MSLD simulation for this system. The project folder is organized into complex and solvent subfolders, corresponding to the complex and solvent systems respectively. If we want to double-check the hybrid ligand structure, we can use VMD to load the PSF topology file and the CRD coordinates file. The hybrid ligand structure can be selected by the residue HYB. Next, we can prepare to run Blade MSLD simulation on a Linux machine equipped with Nvidia GPU. In terms of software, 3 packages need to be installed. First is OpenMM version 8.0.0, and the CUDA device should be accessible. Second is the standalone Blade program patched with Ember improper parameter support. Third is the adaptive landscape flattening ALF package, which controls the sampling in MSLD simulation. We have also made some modification to this code. The original code of the latter 2 packages can be found in Professor Ryan Haynes' GitHub repository. With the downloaded project folder, we can run a Blade MSLD simulation for 2 systems, complex and solvent. For both systems, we need 2 steps. In the first step, we will use OpenMM to do minimization and pre-equilibration to relax the whole system. In the command line, we change directory to this user download folder, then use bash command to run this readme script. We enter letter O to select the OpenMM minimization and equilibration. If OpenMM 8.0.0 is already installed in the current Python environment, we put the letter Y in the second question. In the end, if multiple GPUs are installed, we can specify which GPU we want to use. Such interactive responses can be easily automated using prepared answers in a text file. In the second step, we will use standalone Blade program to run MSLD. We change directory to the same user download folder and run this readme bash script again. We enter letter N to select the MSLD job. The blade command should be accessible in the current terminal, either via the path variable or alias. And the PyALF package should be accessible in the current Python environment. We can also specify the GPU by entering the GPU ID starting from 0. Last, if this is for the complex system, we put PROT. If this is for the solvent system, we put WAT. According to our benchmark on one RTX A5000 GPU, MSLD simulation for this PDP-1B system takes about 37 hours for the complex system and 6 hours for the solvent system. We can finish one MSLD run in 2 days on one GPU card. To obtain a more reliable result, we can repeat the MSLD run for 3 to 4 times. For this example system, we did an MSLD simulation for in total 15 ligands. We also tested different force field combinations. As shown in this figure, most points are within the ±1 kPa region, and the best result is from amber plus GAF force field. Till this point, I have demonstrated how to set up a blade MSLD simulation using our MolCube-Builder platform, and use the generated input files to run the simulation on a Linux machine. Next, I will introduce the OpenMM-AToM method supported by the AFES module in MolCube-Builder. The AToM, abbreviated for alchemical transfer method, is a relatively new alchemical free energy calculation scheme developed by Professor Emilio Galliccio from City University of New York. The major difference of AToM compared with conventional FEP method is in the definition of alchemical perturbation. In conventional FEP, the potential energies of two ligands are perturbed by modifying the force field parameters. But in AToM, the perturbation is the coordinate transformation of two ligands without touching the force field parameters. The AToM method has 3 advantages over conventional FEP method. One is it is more suitable to handle the scaffold hopping situation according to benchmark results. Second is it is easy to calculate the relative binding affinities of two ligands with different net charges, because both ligands coexist in the same system. Third, it does not need the solvent system calculation and could save some computational time. In the AFES module, the setting up of AToM system involves 2 steps, including setting up the pairwise ligand restraints and placing 2 ligands into the system. In this demo, we use myeloid cell leukemia 1 MCL1 protein as an example. Its PDB ID is 4HW3. To set up the AToM calculation system, we use the first protein chain and the first ligand 19G as the native ligand. We use 7 ligands taken from literature, and all of them take -1 net charge. The SDF files of these 7 ligands have been pre-processed so that they have the same conformation and position as the native ligand. We will start from PDB reader. I have shown this step in the MSLD example. One thing different from MSLD setting up is that for AToM calculation, we can use any force field and water model as the main force field. Then we proceed to the solution builder step, which is basically the same as we have shown in the MSLD example. I will also skip the details here, but we will not check this neutralize only option either. Next, we need to click Alchemical Free Energy Simulator in the side panel to use the AFES module. We want to change the MD engine as OpenMM and the calculation type as AToM relative binding free energy. Then we load the solution builder job we just completed and write a name for this AFES job. In the next step, we select the native ligand we want to replace and upload the 7 ligand SDF files we have prepared. The file names of these SDF files should take the format of prefix plus number. We also need to select force field for ligands as we did in the MSLD example. Afterwards, this page tells us whether ligand parameterization is successful or not. In the next step, we can change the perturbation path. Since in the last step, we used the default option to construct the perturbation path centered around the first ligand. The morph pairs in this list all start with ligand number 1. If we click this clustering results button, we can visualize the graph of this perturbation path. We can directly add additional morph pairs using mouse clicks on this graph. Or we can go back to this list and click this Add button. In the middle section of this page, we will see an interface asking for selecting atoms. This part is used to define the pairwise ligand restraint. We remember that we will put one ligand inside the binding pocket and the other in the solvent. But why do we need such ligand restraint if they are not both in the binding pocket? The reason is that these two ligands will swap positions during MD simulation, and adding this pairwise ligand restraint can make sure they have the same orientation, and this could help the simulation to converge faster. To define such restraint, we need to select 3 atoms in a good way. If we use the ligands in this example, we can first find the common scaffold among these ligands. Then we need to find the rigid region on this scaffold, which is this part. The first 2 atoms should define a long axis for this common scaffold. So we pick these 2 carbon atoms as the first 2. The third atom defines the rotation around this long axis. So we pick this carbon atom. So in this atom selection interface, we can select these 3 atoms as primary, secondary, and tertiary atoms in correct order. Please note that the 2D structure here is the native ligand. Once we finish the selection and click the Apply button, it will automatically select 3 atoms for the uploaded ligands. In the next section of this page, we can adjust the position of the second ligand outside the binding pocket. By dragging these sliders, we can change the position of the second ligand. So we want it to stay far away from the protein as much as possible. Last but not least, we can also adjust the simulation temperature. Then we click the Submit button. After the AFES job is finished, we can preview the structure for all morph pairs. Then we can click Download Project. In the downloaded project folder, files are organized according to the morph pairs, and we can run AToM calculation for each morph pair separately. If we want to check the structure of the system, we can open Step 1 Import PDB file for visualization. Till this point, we have obtained all necessary files and scripts to run ATOM calculations. Before we do that, we need a Linux machine equipped with Nvidia GPU and install the OpenMM-AToM package patched with our own modification. Our modification is to allow the OpenMM-AToM package to use ligands in the beginning of the system, while it assumes ligand atoms are after the protein ligands by default. Now we are ready to run AToM simulations inside any morph_x folder. We will first run step 2 bash script to select the target GPU device. Then we will run minimization and equilibration in step 3, followed by production AToM simulation in step 4. After finishing step 4, we can get the final delta-delta-G result from WAM analysis. To get more reliable results, we can repeat AToM simulations 3 or 4 times for the same morph pair. So this is basically how to set up the AToM calculation using our MolCube-Builder and to run it on a Linux machine. Please note that the AToM calculation is a little bit slower than conventional FEP calculations because it needs 2 energy evaluations for each MD step. According to our test on the HSP90 system, it takes almost 2 days on an RTX A5000 GPU. For speed up, we can consider using larger time step and using multiple GPUs for the production run. In addition to Blade, MSLD, and OpenMM-AToM, the AFES module in MolCube-Builder also supports AMBER-TI method. The setting up procedure of AMBER-TI calculation in AFES is very similar to AToM we just introduced, and it is even simpler. However, a big difference is that we can only use AMBER force field in the PDB reader step as the main force field due to the limitation of AMBER-TI engine. However, we can conduct more analysis based on AMBER-TI simulation results, including TI, FEP, and MBAR. Due to the time constraint, I will not go through the details on how to set up AMBER-TI calculation in MolCube service. So, given these 3 alchemical free energy calculation methods, how can we choose according to our needs? If we want to go for speed and rank the binding affinities for a series of compounds with different functional groups but the same scaffold, Blade MSLD is the best choice. If we want to handle the scaffold hopping scenario, or if the ligands we want to study have different net charges, then the AToM would be a reasonable choice. In other case, AMBER-TI as a conventional FEP method is a good choice. In addition to relative binding free energy calculations supported by these 3 methods, we also support absolute binding free energy calculation using AToM method. However, ABFE is not often used because it is very difficult to obtain converged results for molecules with over 10 heavy atoms. So this is what we have in the AFES module so far. I want to briefly discuss about our following plan. As I have shown in today's webinar, the example systems are all soluble proteins. We are currently working on interfacing the membrane builder module with the AFES module so that we can handle transmembrane protein systems later. On the ligand side, we are doing 2 things. First, we are implementing a separate module called the ligand modeler to adjust the conformation and position of user ligands according to a target native ligand. In addition, this will also parameterize these ligands so that we can reuse these ligands in different AFES tasks. At the same time, we are also trying to generate combinatorial structures of ligands with different substituents automatically. Second, we already support GAF and OpenMFF with the accelerated version to parameterize the ligands. We are adding the XFF developed by Crystal Pi to provide another option. In future, we are going to support GrowMax in AFES because this is a very popular MD engine that many people like to use. In this webinar, I mentioned the 3 open source code which we modified. We have released them in our MolCube public GitHub repository. For those of you who are new to MSLD and ATOM methods, I have collected some papers here for your reference. Please note that the recording of this webinar will be available in MolCube's Twitter account. So this is basically what we have today in this webinar.